Welcome to the next lecture on derivatives. So, in the last lecture we started with discussing two important theorems, which are the Rolle's theorem and the mean value theorem. So, let me recall what the Rolle's theorem says. So, let me state the Rolle's theorem. So, the assumption is that let f be a function from a closed interval a b to R, set of real numbers, be a function satisfying the following first is that f is continuous on the closed interval a b. Second assumption is that f is differentiable on the open interval a b, and the third assumption is that the value of the function at the end point, that is f of a, is equal to f of b. And then the conclusion is then there exists at least one c in the open interval a b such that the derivative f prime at c is equal to 0. So, let us understand this by the picture. So, we draw the graph of the function y equal to f of x. What is given is that the value at a and b, the function values are same. So, this is f of a and f of b, and then it is given that the function is continuous on the closed interval and differentiable on the in the open interval a b. Then we claim that the derivative. So, the function might be like this. Here if you see that there is this point where we have horizontal tangent, that means the derivative is 0, or it can be something, it can go down like this and go up. In this case, if you see, there are 2 points where the derivative is 0. So, there can be more than 2 points as well. So, it can be, it goes up and down like this, and then you see that there are all these points where the derivative is 0. So, what we were trying to, before explaining the proof of this theorem, let us try to see that the assumptions in the theorem are necessary. So, the first one says that f has to be, f is assumed to be continuous on the closed interval a b. Suppose f is not continuous on the closed interval a b, then you might have that the function might be just increasing like this, and then I can define at the end point, suppose this is A and this is B, then at A I can define this value. So, this function, there is no C in the open interval A B such that f prime C is equal to 0, and the function here f is differentiable on A B. F is f of A is equal to f of B. F is continuous at all points of A B except at A. So, even if it fails to be continuous at one of the end point, then there need not be any C where f prime C is equal to 0. So, we require continuity in the closed interval A B. The second assumption that f is differentiable, differentiability of f on the open interval A B. So, suppose this fails, then we can have the function might be like this. So, I have A B here, and if you see this function, again there is no point. So, this function is f is continuous on A B, f is differentiable at all except one point in the open interval A B, and f of A is equal to f of B. And you can see that here for all point, let us say this is our point, for any point to the left of this, the derivative is constant positive 1, and for any point greater than this, the derivative is negative 1, but there is no point where at this point the derivative is not defined. So, there is no C such that f prime C is equal to 0. And the third condition, f of A equal to f of B, of course, this also we need, because if I have say just this function, so here you see that the function is continuous on the closed interval, it is differentiable in the open interval, and so if I write f of x equal to say x on the closed interval 0 1, then this is the f is continuous on 0 1, f is differentiable on the open interval 0 1, and if you look at f prime of x, this is equal to 1 for all x in the interval 0 1. So, there is no c where f prime c is equal to 0, but here we do not have, here f of 0 is not equal to f of 1. So, these three examples shows that all the three assumptions in the Rolle's theorem are necessary for the conclusion that f prime c is equal to 0 at some point in the open interval a b. If even one of them fails, then the conclusion need not be true. So, now I will give some idea about why this theorem is true. So, idea of the proof. So, if you note, if you see these pictures, then you can see that these points where the derivative is equal to 0, these corresponds to points of minimum or maximum of the function. Under the assumption of the Rolle's theorem, we can show that there is at least one point C in A B where f of x attains its minimum or maximum value. Now, one fact is that if f is assumed to be a continuous function on closed interval, then it must attain its minimum and maximum value. So, let me write this fact: any continuous function f from a closed interval a b to R is bounded and f attains its minimum and maximum value on the closed interval a b. That is, there exists point x naught y naught in the closed interval a b such that f of x naught is the minimum value, that means f of x naught is less than equal to f of x, and f of y naught is the maximum value for all x belonging to the closed interval a b. Note that the previous result is not true for continuous functions on open interval a b. For example, if you take say f x equal to tan x on the open interval minus pi by 2 to pi by 2, is continuous but there is no minimum, there is no minimum value nor maximum value. Right, this function tan x, you must have seen that the graph of tan x between minus pi by 2 to pi by 2 looks like this. So, as x goes to minus pi by 2, this goes to negative infinity, as x goes to pi by 2, it goes to positive infinity. So, this function is not even bounded, but if we have a continuous function on the closed interval, then this must be bounded and must attain the minimum and maximum value. Another fact is if f attains its minimum or maximum value in the open interval, that is not at the end points, then the derivative at that point must be 0 if the function is f is differentiable at that point. So, here we have a function f, this is defined on the closed interval a b to r, and suppose the minimum or maximum value is attained in the open interval, then there are two cases, either f is not differentiable at that point, or if it is differentiable, then the derivative must be 0. So, example, here if I see this function from 0 to 1 and this is half, the maximum value is attained at x equal to half, but the function is not differentiable at x equal to half. Whereas, if I have the function to be differentiable, if we have something like this, then here again the maximum value is at half. Here if you see, f prime of half is equal to 0. So, we will use these facts to prove the Rolle's theorem. So, first of all, since f is assumed to be continuous on the closed interval a b, there exists points x naught, y naught in the closed interval a b such that f is minimum at x naught and f attains maximum at y naught. This is true for all x in a b. So, this is because any continuous function on a closed interval must attain its minimum and maximum value on that interval. So, now there are two cases. Case 1, x naught and y naught are the end points a and b. So, in this case, but since f of a is equal to f of b, we must have that f of x is a constant on a b, right, because one of these f of a is minimum value as well as maximum value. So, therefore, f of x must be equal to this value for all x in a b, and if f of x is constant, we know that the derivative of constant function is 0. This implies f prime x is equal to 0 for all x in the open interval a b. So, we can choose any c in a b to get f prime c is equal to 0. Right. So, in this case we just have a constant function, f of a and f of b are equal and these are minimum as well as maximum value. So, in this case f prime is 0 at all the points in the open interval. Case 2, at least one of x naught or y naught lies in the open interval A B. In this case, what we have is that either the minimum, if it is x naught in the open interval, either the minimum or the maximum value of f x is attained in the open interval A B. And we have stated this fact that if f attains its minimum or maximum value in the open interval, and if the function is differentiable there, then it must be 0. So, then f prime must be 0 at that point. Because f is assumed to be differentiable on the open interval A B. So, this proves the Rolle's theorem. Okay, let me explain why f prime must be 0 at the point of maximum or minimum in an open interval. So, what we have is suppose we have this point where we have the maximum value of the function is attained at this, and so suppose f of c is greater than equal to f of x for all x in A B, where c is in the open interval A B. Also assume that f is differentiable at x equal to c. If it is not differentiable, then we might have that the maximum is attained there and f prime c does not exist. So, here we are assuming that it is differentiable here, then we want to say that, so claim is f prime of c must be equal to 0. Suppose not, then either f prime c is greater than 0 or f prime of c is less than 0. Now, what happens if f prime c is greater than 0? If f prime c is greater than 0, then this limit of f of c plus h minus f of c divided by h, this is equal to f prime c, which we are assuming is greater than 0. Now, if this is greater than 0, then if this limit is greater than 0, then for small h, this f of c plus h minus f of c by h, this must be greater than 0, because if it was less than equal to 0 for all small enough h, then in the limit this has to be less than equal to 0. So, therefore, we have this implies that f of c plus h is greater than f of c for all small h. Contradicts f of c is the maximum value. Right. So, the derivative greater than 0 will imply that this function must be, the value must be greater than the value at f of c for x greater than c. Similarly, if the derivative is less than 0, then that means that the function at this point it must go down like this. So, similarly, we get a contradiction if f prime c is less than 0. Hence, f prime of c must be equal to 0. So, this proves the Rolle's theorem, where we used one fact that any continuous function on closed interval must attain its maximum and minimum value on it. Without proving it, we assume that, but we proved the Rolle's theorem using this, and then using this fact that the derivative must be 0 if the minimum or maximum value is attained in the open interval. So, next we will prove what is called the mean value theorem. So, the mean value theorem is a generalization of the Rolle's theorem. Here we assume that let f be defined from a closed interval a b to r be such that first f x is continuous on the closed interval a b, and second f x is differentiable on the open interval a b. So, these two conditions are same as the first two conditions in the Rolle's theorem. In Rolle's theorem, we had third condition that the value of the function at the end points are equal, f of a equal to f of b. In the mean value theorem, we do not assume that f of a equal to f of b. Then the conclusion is, then there exists at least one point C in the open interval a b such that f prime of C is equal to f of b minus f of a divided by b minus a. So, note that this is a generalization of the Rolle's theorem as if f of a equal to f of b, then so this mean value theorem will write in short as MVT. Then mean value theorem implies there exists C in A B such that f prime C is equal to f of b minus f of a. So, that is 0, this is equal to 0, that is the Rolle's theorem. So, Rolle's theorem follows from the mean value theorem, but we will prove the mean value theorem using the Rolle's theorem. So, proof. First, let me explain what this theorem says. So, suppose we have this point A and B. I have a function which is continuous on this interval a b, and it is differentiable in the open interval a b. And then let us look at what is f of a. So, this point is a comma f of a, this is b comma f of b. Now, if I draw this line joining these 2 points, what is slope of this line? Slope of the secant line joining a f of a and b f of b is f of b minus f of a divided by b minus a. Then what the mean value theorem says is that there exists some point C where this slope, where the derivative is equal to this slope. So, that means that if you see in this picture, I have this point C. If you look at the slope of this tangent line at this point, this is parallel to this line. That means that the slope is equal to this slope f b minus f a by b minus a. Similarly, in this picture there is another point here, here again the slope is same as this. we need to show that there exists C in A B such that the slope of the tangent line at C comma f of C is the same as, let me call this slope to be m. So, what we want is that f prime C is equal to this slope. So, let us see what is the equation. So, the equation of the line joining A f of A and B f of B is given by, you must have learned in coordinate geometry that the equation of the line joining two point is given by y minus f of A is equal to f of B minus f of A by B minus A times x minus A. So, let us call this line to be L of x is equal to this y, which is f of A plus f of B minus f of A by B minus A times x minus A. And let g of x be equal to f of x minus L of x. So, then we have g is continuous on the closed interval a b, because f is assumed to be continuous and this L of x is continuous everywhere. Also g is differentiable on the open interval a b, again because f is assumed to be differentiable and L is differentiable everywhere. Also, what is g of A? G of A is equal to f of A minus L of A, but L is the line joining this point A f of A with B f of B. So, L of A is equal to f of A. This is equal to, if you put x equal to A here, L of x is L of A is equal to f of A. So, this is f of A minus f of A, which is 0, and g of B is equal to f of B minus L of B. What is L of B? This is equal to f of B minus L of B is again equal to f of B. So, this is also 0. Therefore, g of A is equal to g of B. So, now we have a function g of x which is continuous on the closed interval, differentiable on the open interval, and g of A is equal to g of B. So, we can apply the Rolle's theorem. So, by the Rolle's theorem, there exists at least one C in A B such that g prime of C is equal to 0. But what is g of x? G of x is f of x minus L of x, but g prime of x is equal to f prime x minus L prime of x, and the derivative L prime of x is nothing but the slope of this line. So, this is equal to f prime x minus the slope f of b minus f of a by b minus a. So, therefore, g prime c equal to 0 implies that f prime c is equal to f of b minus f of a by b minus a. This is what we had to prove. Now, we will look at some applications of this Rolle's theorem and mean value theorem. So, one is corollary 1. Suppose f from a b to r be continuous and suppose we assume that the derivative f prime x, this is equal to 0 for all x in the open interval a b, then f must be constant, then f must be a constant. Let x 1 and x 2 be any two distinct point in the interval closed interval a b. We have to show that f of x 1 must be equal to f of x 2. But what we know is that by the mean value theorem, there exists some c in the open interval x 1 x 2 such that f prime c is equal to f of x 2 minus f of x 1 by x 2 minus x 1. This is because we know that the function is continuous in the closed interval x 1 x 2 and it is differentiable in this open interval. Therefore, by the mean value theorem there is some c such that f prime c is equal to this ratio, but f prime x is 0 for all x in a b. So, f prime c is equal to 0. Therefore, f of x 2 must be equal to f of x 1. So, this is one application of the mean value theorem, that if the function is differentiable and is the derivative is 0 on an open interval, then the function must be constant in that interval. So, in the next class we will see some more applications of the mean value theorem, and then we will see some more problems. Thank you.